Thank you
Perfect.
for joining the talk. I'm going to talk about demystifying graph analytics, and what that really means is how do we take these what are sort of complex graph techniques and things that we can learn about graphs by running sophisticated algorithms on them, and turn it into something that we can actually present to an end user and allow them to understand what it is that they're seeing and what insights you may have uncovered. And also, how do we explain them to people who don't necessarily need or even want to know the details behind what we just did to that graph, but really just want to understand what sort of insight that provides? So there's kind of two main thrusts to this talk. The first one is, how do we present graph analytic type data in a visualization in a way that makes sense? And also, what do we do with it? How do we explain and use these techniques in the real world on real data for a real use case? So I'm going to open with a question here. And the first one is, what does this mean? What are we looking at here? Now, if you're a user of Neo4j graph data science like I am, or you're somebody who's familiar with the concept of centrality algorithms and social network analysis, then sure, you probably can figure out what this is. But for most of the humanity, they would have no idea what they're looking at. So the top one is the cipher that's required in order to calculate degree centrality on a graph. And then the bottom one is the actual JSON that gets returned when you call that and you get the results back. What happens is it assigns a score to each node, and this is the node ID and the score associated with it. But you're never actually going to do this. You're never going to show this to somebody and expect them to understand what it is that they're looking at, or expect them to make any decisions based on this data. So the centrality and degree centrality is a really powerful thing, but you have to actually present it in a way that helps somebody understand what they're looking at and make sense of it and make decisions based on it. So what I'm going to do today is I'm going to talk through a few different graph analytics algorithms, and then also actually show you visualizations which present that in what's hopefully an enlightening way. And then also talk about some cases where using that type of technique might make sense. So the one you saw in the previous slide was called degree centrality, and it falls into a category of centrality algorithms, which fall into a broader category of what's called social network analysis. And what that's really aiming to try to do is to understand which nodes are the most central in your network, which ones are the most well-connected. But central could mean a bunch of different things. And there's a whole bunch of different ways of calculating what central is, depending on what it is that you're actually trying to uncover. And degree centrality is really the most simplistic of it, and it's the easiest to explain and the easiest to understand. It's basically just a score assigned to each node for how many links it has. And the nodes that score higher are probably more central to the network or more well-connected. And we call this social network analysis because it was originally designed to look at networks of people and how they might be talking to one another, or communications or things like that. But the whole concept has evolved such that you can run this on different types of graphs that don't necessarily have to involve people or social connections at all between them, and still get interesting and valid results. But for the purposes of today, I am going to stick with networks which are comprised mostly of people and relationships between people. So the reason you might want to calculate degree centrality is to present to somebody, these are the nodes that are the most important in my chart, the most well-connected, the ones that maybe you should pay closer attention to or want to focus on. And there's a couple of different things here. You can just calculate the sheer number of links associated with each node, or you can weight them by some sort of property on the link. So over here in the screenshot on the right, I've got a network which is comprised of individuals in an organization, and the links are the emails between them. And let me show you a live example where we've taken degree centrality and we've turned it into a graph. So this is the same data we were looking at earlier. We've got a bunch of different people, and we've got links between them when they email one another in our data set, which happens to cover a couple 100,000 emails between these individuals. And we've modeled that as a graph, obviously. So each node is a person, and the link between them is the email. Now, degree centrality is just going to count the number of links associated with each node. And what can I do with that information? Well, I can just show that count to an end user in a table. That's what I did at the beginning with that JSON object. But what I like to do in the visualization, and you can do this with Bloom or with a bunch of other tools too, is tie that to a visual property of the graph itself. So if I calculate degree centrality here, I've taken the size and the color of the node, both of which are pretty useful metrics to associate with the centrality of a node because they stand out visually. And you can see the nodes that got larger are the nodes that have the most links. Now here I'm just using the simplistic metric of calculating the number of links associated with each node. We can make it a little bit more complex. So right now, a link is a link between two people. They've emailed one another at some point in our data set. But it doesn't take into account whether that's 1 or 100 or 100,000 emails between these people. And that strength of the connection can really make a difference. So if I take that into account, what I did was I did two things. I assigned the width of the link to bind to the number of emails between these people. But I also told the degree centrality algorithm to take advantage of that so that links that are thicker, because they represent more communications between those people, are weighted more heavily. So I'm not just counting the number of links from each node, but I'm counting the number of emails from each node. And you got to see the nodes change size here. So while previously everybody in this group was roughly the same size and color, when I used degree centrality and chose to take advantage of the link width or the number of emails, Tana Jones stands out quite clearly as being the biggest communicator in this network. She's both sending and receiving a lot of email in this data set. So degree centrality is a really simple calculation. It usually can run quite quickly even on very large data sets, and it can produce pretty interesting results, and it can allow your user to identify very quickly in a visualization which nodes it is that they might want to focus on or pay more attention to. The next one we're going to take a look at is called closeness centrality. So if I go back to the days about 10 or so years ago, actually closer to 15 or so years ago now, where I was working with the US intelligence agency, and we were assembling graphs based on intelligence we'd gathered from criminal gangs or terror cells or things like that. And I was using social network analysis algorithms to try to identify, based on the intelligence we'd assembled, what the most important nodes were, who's the leader of this organization. And closeness is one of the ways that we do that. So what closeness does is it says who has the most reach throughout the network. So it's not just sheerly counting the number of links associated with each one, but it's saying how far away from each node in terms of how many hops do I have to go in order to encompass the entire network. So it's a sense of how big the reach is across the entire network for each node. And a corollary to that is which nodes, if I were to remove them from the network, would most disrupt the shape of the network. So if I were to take people out of this network, how disruptive would that be to the network? How difficult would it be to communicate if this were a criminal gang? So I think of closeness kind of as a targeting metric. Who is the most important person if I were to arrest them, or potentially worse if this were a terror cell or something like that? And who's likely to cause this most disruption? And that might not necessarily be the leader of the organization. It could be somebody who's responsible for communicating across different parts of the organization or holding the whole thing together like glue. So let me show you two examples of this. So the first one, if I go back to this previous example here, and instead of calculating degree, I calculate closeness, you see that the size and shape of the nodes changes. So the larger nodes now are showing me who has the most breadth and depth throughout the network, who's going to encompass it all. In this case, it still is Tana Jones, because she's so well connected to other people themselves are well connected throughout the network. And so if I wanted to remove somebody from this network, then Tana Jones might be the first place to look. But let's look at another example now here too. I've got an example that's showing me a network of mafia members in Sicily. So much closer to the kind of intelligence gathering that I used to do here. So these people are colored by being representative of various families, and they're sized and colored by their closeness score. But what I can do is remove nodes from the network and see how the network changes. So if I pull out the largest node or the largest two nodes, I can see what changes. And I can see if I go all the way up to I have to take out the largest 10 nodes before I really break this big segment into two different sections. So if I take out those people, now all of a sudden I've got two separate groups who have no connections between them. And the layout is allowing me to see how that might change the structure or the shape of the network based on removing those. So it allows you to play these kind of what if games. So now let's take a look at another one here. I'm not going to go through every centrality algorithm. There's well more than a dozen. And at some point, they all start to do the same thing. But betweenness centrality is interesting because while I thought of closeness as sort of the targeting algorithm, who should I remove from the network to cause this most disruption, break it up into pieces, make it so that they can no longer function. Betweenness is more of a surveillance type algorithm. Who might I want to pay closer attention to or look at the data that's going in and out of that node to try to learn as much as I can about the workings of this network? Who is the most likely to have information flowing through them? And the way that's calculated is it looks at the shortest path between every node and every other node on the chart. And it says, how often is a specific node on that shortest path? So something out here on the periphery of the network is never on the shortest path between two other nodes, but somebody that's here in the middle could be acting as a funnel or a conduit of information or data as it flows across the network. So let's go back to the example I was showing you previously with the network with Tana Jones here. If I were to switch this over to calculate betweenness, now I'm seeing that the largest, reddest node in this network, because it has the highest betweenness score, is John Lavardo. So in this network, if I were interested in trying to pay attention to the data flowing in or out of a node, he might be a good place to look. And you can kind of see that visually in the example, because if somebody out here that's in, say, Tamara Black's section of the network needed to communicate with somebody down here, in Kimberly Bates's section of the network, it looks pretty clearly like they're going to have to go through John Lavardo in order to do that. He's going to be the way that data flows from those disparate parts of the network. So a good place to start investigating if you want to understand the the funnels or conduits of information as it flows across the network. Okay, the next thing I'm going to move on to is outside the realm of centrality. And centrality is all about trying to uncover the most central nodes. But there are other things that you might want to do in your network as well. So you may want to uncover clusters. Now, a cluster is defined as a group of nodes who have more internal links to other nodes within that group than they do externally to other members of other clusters. And there's a bunch of different ways you can calculate how to find those clusters, but they generally come up with similar results. So over here on the right, I've got an example that shows the members of each cluster color-coded, and the calculation, which is trying to uncover what those clusters is, has done a pretty good job of being able to recognize that this is an isolated group, which is pretty obvious because it has 0 links to anybody outside of this group. This one is a separate group, this one here in orange, because it has only 1 link to the members here, which are in blue. As you get very tightly connected networks, where every node is connected to a large number of other nodes in your network, the clustering algorithm doesn't work as well. But that's also useful evidence to say maybe there aren't independent clusters or groups in this network that I want to pay attention to, or that might be useful for analysis or visualization. So in this case, we've assigned a unique color to each cluster, but you do have to be careful about doing that, because by assigning a color to each cluster, you're sort of implying to whoever's looking at this data that there's something in the data that is saying that these are somehow different. They're of a different type, or they represent a different property. But that may not be the case at all. That may not even be true. The algorithm itself is the one that's determining that these might be members of different clusters. But we don't know that they actually are. We don't know that we might be missing data, or that the colors don't actually represent anything inherent in the data itself. And then we can group by clusters too. So this is useful when you have a really complex data set and you want to simplify the view of how you're presenting it to the end user. So let me show you an example of this. So in this example, this is where I was showing you the clusters before, and it's the same data set. So we've come up with the same clusters with the various colors representing each one. And it's a complex data set. You might necessarily need to, and especially as the amount that you're visualizing grows, look at each individual data point itself. So if I group here, what I've done is I've created a group based on each cluster. I've represented that entire group as a node. So I still have the general structure of the graph in my visualization, but I don't have the representation of every single individual node shown. So I can see, the clusters which are well connected to other groups on the chart, the ones which are less well connected are out on the periphery of the chart. But if I do actually want to look at that individual data here, I can actually open up the clusters and look inside of them. So now I can see, this group here, which is these sort of greenish type nodes, are connected internally to other groups here, which show the members of those clusters. So you can have as complex or as simple a visualization as is helpful for you or for your end users. But you do have to be careful with this grouping too, because the grouping by cluster, again, it even more so than the color is implying that there's something in the data which is causing you to create these groups. They're members of the same family, or they're representative. They live in the same country or town or something like that. Whereas that's not actually true at all in this case. They're being grouped together because they are similar in structure to the other nodes in that cluster, not because they share any property intrinsic to that node itself. So I do like the clustering algorithms, but you do have to be really careful there that you're not showing something that you didn't intend to, or creating an implication that isn't actually in the data. The next one is paths. Now, it is one of the reasons that you use a graph database is to be able to do these sort of traversal type queries. And oftentimes that's because you want to understand the shortest path. How can data flow, or how can something flow from one node to another on the chart? But again, there are a couple of different ways that you might want to show this to the end user, but it's not inherently obvious if I just give you a list of the nodes that represents the path between these two, or the shortest nodes, the shortest path, then that's going to be actually useful to somebody. You can show that on the graph to say, this is the shortest path between these nodes. And I think that that's a reasonable way of doing so. But you have a limitation in that you don't necessarily, in many cases, want to show the entire data set to somebody just so that you can highlight the shortest path between the items. The other items that aren't on that path may not actually be relevant to your end user who's trying to understand what they're uncovering in the data here. So let me show you this too, because I think the way that we've animated this example is pretty interesting. So in this case, this is like a example from the back of a road atlas, which road atlases don't even really exist anymore. But back in the day, you could go to the back of it and it would show you cities which were connected to each other, and maybe the distance between them in miles, or how long it would take to drive between those two cities. So if you're planning a road trip, you would want to identify what the shortest path was between these two. Now we all just turn on the GPS. But if I wanted to, in my graph, figure out, how do I get from Toronto to Richmond? We've used animation and the shortest path algorithm, and the width of the link, the color of the link, and the border of the node, all to identify what that path is. So you actually got to watch the path flow from Toronto to Richmond and identify that shortest path. Now, that path can be calculated a few different ways. It can be just simply what's the fewest number of hops between those. It can be, in this case, trying to minimize some property of that that's on the link. In this case, maybe the distance, the mileage distance between those two cities, or the drive time between those two cities, or sheerly just the number of hops. Now, different ways of calculating it can show different ways of presenting that to a user. So in this case, we've chosen to do the color to show based on how we are actually calculating that shortest distance. And I think the animation there can be really powerful as well. Now, the other piece is the shortest number of sequential paths, because so far we've really only been talking about graphs and the node link representation of graphs, and how do I visualize those, and how do I represent things on a node link visualization. And those typically aren't very good at showing times or sequences. And a lot of times your links are going to represent events. This is something that happened out in the real world, and those things happen at times. So I may want to know not just what's the shortest path between Ella and Josephine in this example, but what's the shortest path that something could have actually taken. So in the email example, the emails are actually events that all have a date timestamp associated with them. But if I'm saying, how did information get from somebody in the top part of this network? If I go back to my social network example, we were talking about information flowing from Tamara Black down here to Kimberly Bates. Well, if I'm interested in the path that might have taken, obviously every sequence, every subsequent email has to have been sent after the previous one. There's no way that John Lovardo could have sent a message to somebody down here in the bottom section of the network before that message actually arrived at him. So when we're looking at the shortest path, unlike when we did so with the drive time, where we don't necessarily care about sequences, oftentimes we do want to know what I call the shortest sequential path. So that's kind of what we're seeing down here in this example. We're saying, find me the shortest sequential path from Ella to Josephine. Well, we can't take this first link into account because, first of all, it's in the wrong direction. We can't take this red link into account because it happens before anything flowed to John. So John talking to Josephine at that point isn't relevant to my query. The shortest sequential paths are the ones that I've highlighted in green here. Ella speaks to Nathan, who then speaks to John, who then speaks to Josephine. And that's not necessarily the shortest path, even in terms of sequence, because we have a previous example here of Josephine talking to John, but that's the wrong direction. So that's not what we're looking at. So we might have a directed network too that can make a difference here. So for those types of things where we're interested in the timing and the sequence of items that are coming from our analytics and trying to present those, I think a timeline, or a timeline combined with a traditional node link representation, can be really valuable. So what I've done over here is I've created a timeline on the right, which represents money flow, transfers between various accounts. And over here on the right, we're showing the same thing in our node link representation. So I've got $7,500 going from a casino account to a checking account. But if I'm interested in perhaps uncovering fraud or trying to discover how the money is flowing from one node on this chart to the other, then the node link isn't going to tell me that. If I look at this example here of this $9,000 flowing from one checking account to the other, the timeline is what is showing me the actual transactions that are represented by that link, which in this case is not even just a single transfer. It's several different transfers which all sum up to that value over the course of a few different months in 2021. So by combining a timeline type view of this data with a node link representation of the same data, you can really present things like shortest path or things like shortest sequential path in a way that stands out. It makes it pretty obvious to an end user who doesn't necessarily have to know how the algorithm works, what it is that they're looking at. And then the last one that I'm going to go through here is what we call all paths. And we get asked for this a lot at our company. How do I find every single path between these two nodes? Because I'm interested in what are all the different ways that data could have flown from one node to another over the course of the data set that I have. And there are absolutely some use cases where this can be a valid question to ask, but I've found that more often than not, it's actually not that helpful. And the reason why is because eventually all paths is very likely to encompass every node on the chart. So if we look at this example here, a naive example would just say, well, how do I get from node 1 to node 6? Well, I could go 1, 5, 4, 6, or I could go 1, 2, 3, 4, 6. But in reality, there's every single node could be involved in this path. I could go 1, 2, 3, 4, 5, 4, 6. I could go 1, 1, 1, 1, 1 because of that self link, 2, 5, 4, 3, and then just go around that loop as many times as is necessary to get to 6. And I found that in a large number of examples like this, when you are interested in all the paths between two nodes, you do find that that's not always the most useful question to ask, because it's every node on the chart could be a member of that path at some point. It can be helpful if you have directed links and you have a very sparse chart and you're only interested in a path that takes the direction into account. Or it could be interesting when you have a sequential type scenario and you're interested in only links that occur after the other. That would vastly cut down on the number of paths that you want to show, the number of possible paths in your network, and you want to show those to an end user. So I want to take a step back and just talk a little bit about the tools that I've been using here in the visualization. So everything that I've shown you today in terms of how to present the results of graph algorithms to an end user can be done with really any number of different visualization tools. You could build something yourself with D3. Bloom has a lot of this capability as well. What I've been using is our tools, toolkits, which are called Keylines, Regraph, Chronograph, and they are for embedding inside your application. So if you want to create an application and white label a component to do graph visualization or timeline visualization inside of those, then that's what we do. And so we specialize in the ability to take complex graph data and present it in a meaningful and useful way to an end user. Keylines is our JavaScript toolkit. Regraph is our React toolkit, which accomplishes basically the same thing, but it's designed for React developers and in a very reactive kind of way. And then Chronograph is our timeline piece, which I showed you a little bit of today. So I left some time at the end here to answer any questions that you might have. So feel free to ask questions now in the chat. And as soon as I stop sharing my screen, I'll be able to see those. But also do feel free to email me afterwards if you're interested in taking a closer look, or you have any questions about how to visualize something or anything else that I've presented. I'm more than happy to answer anything that you might have. And thank you very much for attending. Okay, so I'm taking a look at some of these. There's actually quite a few, so I may not have time to get through every single one of them. But let me see. I did talk a little bit about some of the other tools. D3 is an example that comes up a lot. It's really powerful. It does require quite a bit of development expertise to get something that's useful. But once you do, you can do a lot of this with building it yourself. Obviously, you can use our stuff too, but I'm not going to try to sell you on that. Another question I see here is around the size limit. A lot of that depends. I'm doing in-browser, in-memory visualizations. So all of these things are stored in the browser, and I'm presenting them with JavaScript and Canvas and WebGL. What that means from a practical standpoint is once you get into the high tens of thousands of chart items, nodes, or links, you start to get some frame rate issues, especially when you notice you want to run animations and things like that. A lot of that does depend on the client-side hardware, and a lot of it depends on the tool that you're using too. So something which uses SVG might start to bog down a little bit earlier than something that uses WebGL. I see a question from somebody who's really interested in the Road Atlas. Yeah, I still have my 2008 Rand McNally Road Atlas, which is the last year that they actually put it on paper. I can't say I use it that much anymore, but that's where I got the data for the demo I showed you. A question about whether it's possible to integrate what we have with Neo Dash. My answer is probably yes. I've actually never tried to do that, but I believe that could be done, but I'd have to take a closer look. Okay, I think that's all. There are some more comments here, but I just don't have time to be able to go through all of them. But I will save all of these, and I'll try to reach out to anybody that has a question with the answer offline. Thank you very much for attending. I really appreciate it.